They were part of a supercontinent geologists call Gondwana land. Glossopteris was able to spread across this ancient landmass. But then, Gondwana was split up by violent tectonic forces, which pushed the continents apart. And 80 million years ago, India broke away from the supercontinent. It traveled north and eventually smashed into Asia. To get the full picture, geologists now knew they must get an exact date for this collision. Once again, they turned to marine fossils.
We know the age of collision of India and Asia from several factors, but the most important one is the age of the youngest marine fossils that are preserved along that collision belt. And the age of those fossils is very precisely dated, 50.5 million years.
80 million years ago, India left Gondwana. 50.5 million years ago, it hit Asia. India traveled 4,000 miles in just 30 million years. Very fast in geological time.
India was drifting northwards across the Indian Ocean at very rapid plate tectonic speeds. And we're talking here between 10 and 12 inches per year, which is very rapid.
It's this speed that goes some way to explain the unique size of the Himalayas. Because, as with any smash, the faster the collision, the bigger the wreck. The investigation has now uncovered clues to prove India and Asia were once separate. Ammonites are evidence that an ocean once existed between India and Asia. Glossopteris fossils prove that India was once part of a supercontinent called Gondwana land. The next part of the investigation is to discover how this intercontinental smash gave rise to the tallest mountain in the world. Geologists piecing together the story of how Everest was made have shown that 400 million years ago, a wide ocean existed where the Himalayas now stand. India was part of Gondwana land until 80 million years ago, when violent tectonic forces threw the planet into turmoil and split up this ancient landmass, pushing India northwards. 50 million years ago, India collided with Asia. And for the next 30 million years, this intercontinental smash began to shape the world's highest mountains. Traces of the first stage in this process can still be seen in the Himalayas today. The best way to spot them is from the air.
Because the high Himalayas are so incredibly inaccessible, I mean, just look at that view out there. There's a sea of mountains. All of them are over 20,000 feet. There must be hundreds of them. And those are impossible mountains for a mere mortal to climb.
This is geology on a massive scale. The distinctive formations come into view. Huge folds of rock, clearly seen on the sides of the mountains.
All of these folds that we're seeing right here on Dhaulagiri and Tukche Peak were formed during the first part of the Himalayan mountain building process. So when India first collided with Asia, the first thing to happen was that the northern margin of India started buckling and folding. And those folds are just so spectacular. When you look out the window here, they're just unbelievably impressive.
Like a giant train wreck, India collided with Asia. The land and ocean floor that lay between literally folded up under the enormous pressure. But folds are only part of the story. Alone, they don't explain the Himalayas' vast size. Back on the trail, Searle is on the hunt for further clues.
This is what makes the whole trip really worthwhile. We've just spent 5 days hiking up through the jungle, through the forest, pouring with rain, And up there, finally, are the high Himalayas. I just love those mountains. Look at those peaks up there. They are absolutely beautiful.
Searle points to an intriguing giant scar which is revealed on the face of one of the mountains. It's evidence of the next dramatic phase in the building of the Himalayas.
This is a sketch of what we're actually seeing in front of us, with the big mountain of Dhaulagiri here and the big folds on the peak of Tukche to the right, with this enormous great fault that is magnificently exposed right along the base of Dhaulagiri, coming right down to the Kaligandaki river valley at the bottom.
The fault is a fracture running right through the mountains.
Well, the first step in deforming the Himalayas is that the rocks are folded into giant folds. And when that process continues, the rock can no longer fold, so they become overturned folds. And when the process continues even further, that overturned fold actually moves along a very discrete fault plane. And that's exactly what we see throughout the whole Himalayas. So rocks are formed by folding and thrusting.
Rocks can only be bent so far. Once rock has been bent beyond its limits, it breaks and causes a fault. The process of faulting puts different rock types one on top of the other.
Faults are juxtaposed rocks of two different types. So the big, huge fault that cuts through the tops of the high Himalayas, the top of Everest, are rocks that are putting limestones over marble.
This is exactly what was revealed by Kenton's rock samples from Everest. Limestones at the summit, lying on top of the hard marble of the yellow band. Evidence that the top of Everest was initially created by folding and faulting. But this only explains part of the story. To create a mountain the size of Everest, geologists knew that there must have been another, more powerful mountain building process at work. Clues to exactly what this process was can be found in the Kalemdikola River.
This river is a giant garbage chute, bringing all these boulders eroded off the high Himalayas to the north and sweeping them down in great floods down to the plains of India to the south. So this was a great place to come to sample all the rocks that make up the high mountains to the north.
As any detective knows, some of the best finds are made by sifting through garbage. This time it's garbage from the Himalayan peaks.
This is exactly the rock I've been looking for. This is a beautiful example of a kyanite gneiss, which is composed of these beautiful blue bladed crystals of kyanite.
Kyanite is a gemstone, and it gives a clue as to how these rocks formed.
This mineral is very specific to a geologist, and it tells us that this rock has been buried to depths of about 30 miles or more under high temperature and high pressure.
Rock was not only pushed upwards by the collision, but also down towards the Earth's molten core. Heat and pressure changed the rock and formed kyanite crystals. Another boulder in the river gives a further clue as to what was going on at these great depths.
This white rock is a Himalayan granite, and most of the highest peaks of the Himalayas are actually formed of this rock. And of course, the base of Everest is formed of exactly the same. The presence of these white streaks tell me that this rock was actually partially molten at the highest temperatures during the Himalayan mountain building process.
The rock was pushed so far beneath the Earth's surface that it reached heat in excess of 4,000 degrees Fahrenheit and began to melt. Once it was molten, it was able to move and flow.
Well, you can think of the Himalayas more as a conveyor belt system, taking Indian plate rocks, pushing them down deep in the crust. They are altered by heating and increasing pressure, eventually melting to produce granite, and then forced back up to the surface along these giant shear plains.
20 million years ago, this amazing conveyor belt system was at work. As India pushed northwards, a liquid band of buoyant rock was forced towards the surface and cooled, forming a solid layer of granite. A process called channel flow.
Granite's a very buoyant rock, so when they're formed by partial melting of the crust, normally they're pushed up through the crust to form mountain ranges like you see in the Sierra Nevada or Yosemite National Park, for example. The Himalayas are different. These granites are flowing almost horizontally from where they formed the southern part of the Tibetan Plateau to form the high peaks of the Himalayas. And it's this conveyor belt system that keeps the high Himalayas actively uplifting to this day.
The mountains were repeatedly jacked up to epic proportions. It's this unique process which accounts for the Himalayas' immense size. Kenton Kuhl's mission to Everest uncovered an unusually thick band of granite. Proof that Everest's awesome size is due to the process of channel flow. Geologists investigating how Everest was built have discovered folds and faults, proof of the initial mountain building process. White stripes of granite indicate the rock was melted at over 4,000 degrees, forming a giant conveyor belt of mountain building power. But the Himalayas were set to become part of a geological battle between catastrophic forces and powers which would challenge the very height of Everest. 400 million years ago, the Himalayas started out life at the bottom of an immense ocean. 50 million years ago, they were thrust into the skies as India smashed into the Asian landmass. Since that time, tectonic forces have created the tallest mountain in the world. But what of the immediate future? Will Everest continue to rise, or will this giant soon be cut down? John Galecka is investigating whether the processes which built Everest continue to this day. He has traveled to the remotest regions of Nepal and India, setting up GPS stations, which he hopes will provide him with the answer.
All right, come as far as I can by car, and I've got a 3-hour walk straight up the slope.